Good evening, ladies and gentlemen. My name is Pranav Sharma. I'm a science historian. I'm the in charge of the project on documenting the history of Indo-French scientific partnership. It's a very interesting project because it's for the first time we are really delving academically into the intricate details, the nitty-gritties of the Indo-French experience of science. Having said that, because this is the Gender Equality Month, we thought it would be of great benefit for our readers and listeners, our friends, family, and people that we know to give a glimpse of what it means to be a woman scientist in the world. Um, for panelists of today, I would like to go back on um, the way her field started, especially in India. High energy physics has been of great interest to Indian physicists, to various academics in the 20th century, especially in Asia. There were people like Shanti Swarup Bhatnagar who hosted experiments in Gulmarg in Kashmir. Then there were scientists from Bombay who got trained by uh, Irene Curie and Julio Curie in the Radium Institute in France. Then there were people like Bernard Peters and Yashpal and Homi Bhabha, who had French colleagues, helping him establish the program. Much later, we see this wonderful young woman coming out of Jhansi, who reaches BHU, gains her uh, primary training from BHU, comes to Delhi, then does her doctoral work there, gets really enchanted by the high energy physics field, goes to Geneva, and now she is among the top science policymakers in the world, and she's done immense contribution in the field of high energy physics experiments, especially in concern with the CMS experiment. So today's speaker, we have Dr. Archana Sharma, who's the principal scientist at CERN. Uh, we are very happy and we're very happy to welcome you, ma'am. Uh, First of all, we would like to hear from you about your research, about your experiences and your life journey. And then perhaps towards the later half of the discussion, I would have some questions that we can engage.
Thank you, Pranav, for that very generous welcome. And in fact, you are painting a picture which is really far beyond whatever I have done, whatever little I have done. So thank you very much once again for inviting me and giving me this opportunity to speak about my work, my experiences, and also a little bit about the contribution that we all have made together in the field of particle physics, particularly. So I will just share my screen. So my screen is visible.
Yes, yes.
Okay, so clearly we all begin with curiosity. When we are small, we have so many questions. We ask our parents, we ask our friends, colleagues, uncles, aunties in the society. We continue to have so many questions about where did we come from? Where did the universe come from? When did it begin? Where is it going? Is it going to end? And all kinds of questions that come in the minds of young children, they continue even today. And here I would say that there is no difference between being a girl or a boy. I think up to a very mature age, all development is very, very similar. So I think in the humble state of things, our duty is to encourage young girls particularly into this field of physics, particle physics, which has the, let's say, the bad name that it's a very difficult field and it's a very complex field. It's for geniuses, it's for people like Einstein. And I'm here to prove that wrong, that if I can do it, I think that anybody can. Yes, I am at CERN, as you mentioned, Pranav. I am here since over 30 years now, and this is an institution which is very close to my heart because apart from what I learned and prepared the foundation in India, a lot of what I learned comes from here. And again, it starts by questioning what is the nature of our universe, what is it made of, and in this very beautiful artifact that is standing outside the CERN complex, we also see many, many Indian contributions in this particular artifact of the evolution of science, starting from Pythagoras, Archimedes, up to the Higgs boson. So these are beautiful things which help us continue the tradition of curiosity and questioning our own selves about these open questions. In physics, particle physics in particular, the open questions are: what is the origin of mass? Essentially, where did we come from? What is dark matter? And we have heard about black holes, and the LIGO experiment also has measured the gravitational waves that came about a few years ago. And there have been tremendous strides in our understanding, but nevertheless, there are open questions. Why at all are we here? Why is there matter in excess over antimatter? Why did it not annihilate at the time of the Big Bang when the whole universe began? And what is this primordial plasma, or the soup of particles, or the soup of matter from where we all come from? All of us are related to each other because we come from the same soup, from the same primordial plasma soup. So we need to look at answering these questions, though they may seem very esoteric, but they bring with us a lot of opportunities, not only in the theory and experiments that we do in nuclear and particle physics, or high energy physics as it is called, but also in building relationships, building partnerships, doing research together. And that's where, like you mentioned, the gender aspect is very, very important, because without collaboration, we would not be able to do any of these very big experiments that we have been able to do over the last many decades. So CERN, as such, is an acronym for Conseil Européen pour la Recherche Nucléaire. And the name has stuck, the nuclear name has stuck, because this was in the early 50s when scientists were running to the United States from Europe, and European countries got together, 22 European countries got together, and they created this forum, and they created the organization, like an international organization, which is called the Conseil Européen pour la Recherche Nucléaire, because that was nuclear physics at that moment of time. Today, it has evolved into particle physics. And the big pillars on which science and CERN sits is research, collaboration, education and training, and of course, with all that comes technology and innovation. And the impact of technology and innovation is unbelievable, simply because you and me and all of us together, we are right here connected because of technology. And in this world, in the situation that we are in, the pandemic situation, it is incredible to imagine a world without science and technology. So it is indeed for the humankind, for progress of societies, for countries, that we absolutely need to partner, and we need to continue this journey of mega science experiments. And CERN is one such mega science experiment, where scientists come from all over the world. Then they get together, they keep thinking about what is the next thing to do, and so on, and what are these challenges, picking up one challenge at a time. So we need to answer questions. Where did we come from? What is mass? And for that, we need first to create some models, which means that we need also mathematics, theoretical physicists who come again together, and we need experimentalists who also come together from all over the planet, who push the limits of technology and create machines that can first recreate on a very tiny laboratory scale, the Big Bang. What does it mean? We are going back in time, and we would create that minuscule nano auto, whatever, smallest Big Bang, and we would measure the primordial plasma. We would measure what's happening at that moment of time. So in that sense, we are little detectives, and we go back in time trying to answer these questions, which are going to give us a lot of technologies, a lot of societal impacts, and a lot of dividends over a long time. And of course, on the path, we might discover something like, you may have heard about the Higgs boson, and we build the largest apparatus on the planet. The World Wide Web, as you know, was also invented at CERN. We create antimatter. And of course, we have future machines like the high luminosity LHC, which I will not go in detail. But for all this, we are secrets of the universe, recreating the conditions of the Big Bang and trying to understand the recipe by which that soup was made with scientific research, with cutting edge technology, and we have to obviously do R&D. The LHC, the Large Hadron Collider, was conceived in the early 80s, and it started operation for the first time in 2008. So just imagine the compelling engagement of scientists, physicists, technologists, engineers that was needed to bring that project into fruition. So this is the message that we would like to take forward in understanding the constituents of matter. All of us know this picture very well, where how we are made out of atoms, out of electrons, protons, and protons themselves are not the smallest constituents, but they are made out of smaller particles, which are called quarks and leptons, like the proton and the electron. And how do we know this? Because we have been doing some experiments. So let us do an experiment, and we are all together partnering in this experiment. Let us build 2 helicopters, and these helicopters are made out of little pieces of Lego. And when they collide, they break down, but they do not break down into the individual smallest particles. Why? Because the energy that was given to these 2 helicopters was not enough. So what should we do? We need to increase the energy, isn't it? So then we will be able to find out what are these helicopters made of and what is the smallest particle with which these helicopters are made. So let's do that experiment. And what happens this time? Because we have increased the energy, we get the smallest constituents of the helicopters, Lego helicopters, but we still do not know. Once we have all the constituents, we will not be able to say what did they make, right? We would not be able to say that they were helicopters before. So this is a mystery that is on both sides we have to go, which means we have to look inside the matter, and then we have to look outside as well, that what has been the evolution. And in doing these kind of experiments, looking at radiation, looking at particles that we cannot really see, but we have been able to find a large number of elementary particles. And we know that these elementary particles, they come in 3 families, and they have interactions among them. Just like you play with magnets at home, you know that if there is a spoon and if there is a magnet, they could be attracted to each other. Similarly, our particles, they behave under strict laws. And those are forces, the four fundamental forces. That's gravity. You all know when you jump, you fall down. That is because of gravity. Electromagnetism, the strong force, the weak force as well. And we can live on Earth, we can have the day and the night and all the life around us because of these forces. So, isn't it very important to study this standard model of particle physics? It's just like the periodic table of chemistry, except that it's a slightly more complicated. But nevertheless, it's not impossible. We can write this whole standard model in one equation that fits on a t-shirt, or it fits on a cup in which you have your coffee or tea. So it's not that complicated, right? So let's continue our experiment. We are having fun together, I hope. And when we increase the energy of these two helicopters, what happened? Not expecting this, were we? What do you see? You see dinosaurs. And this is incredible because we started with helicopters and we got dinosaurs. What does it tell us? We do believe in dinosaurs, and we do believe in dinosaurs because we have seen fossils, we have seen remains, we have seen signatures. In the same way, when we build our time machine, we can recreate the conditions of the Big Bang and we can create dinosaur particles. By giving energy to the basic constituents like protons, we can accelerate the protons to a very high degree, to such energies that when they collide, they recreate temperatures over 1 billion times higher than those prevailing at the center of the sun. And they can also produce particles which which may have existed at the time of the Big Bang, but they do not exist anymore. So you see, just like the dinosaurs, we can produce a whole plethora of particles which we could expect when we do our experiment, or they could be hypothetical. They could be just given to us by theory and we did not know that they could exist. We have unsuspected particles and we have the extinct particles like our dinosaur particles as well. So you can just see this cartoon here where you've got very known particles, or we call them, you can see this is just to explain the analogy that you can see butterflies, tortoise and cats and dogs, etc., while you see aliens and stuff too. So that's our big dream in our machines, that when we go and we have our accelerator switched on, can we make one of those particles? That's really the thing that scientists and engineers and technicians and physicists, everybody is pushing forward to find that something in the theory, in our standard model, that can explain from where we got mass, for example. This search definitely requires a lot of things. It's not that simple. So accelerators, they are very powerful machines. We need accelerators so that we can give so much energy to the protons, a lot of them, not one or two, but millions and billions of them, in fact, in bunches that can come together and they can smash with each other. Then we need photographic cameras, which can take pictures of these collisions, and they are called detectors. And they can record everything that's coming out of these collisions. So that on one side, we know that the energy that we have given to the protons, E, and you all know one equation that is called E is equal to mc squared. So on the other side of the equation, we will measure the mass of every particle that is coming out with the help of our detectors, our cameras, and we will add them together. And you know that this equation must be balanced, right? So we will be able to find that special particle that was created, which we did not know, which we did not know that which does not exist anymore and existed at the time of the Big Bang. So we are hoping to find something like that. For this, we need a lot of software, a lot of very smart algorithms. We need machine learning. We need a lot of stuff in computing, so to speak. We, of course, need people. And this can only happen on a collaborative scale, in a partnership across the globe, and thousands of people come together to make this accelerator and the experiments that we do together. This is the largest microscope on the planet, 27 kilometers in circumference. And you see two beam pipes here. You see there are the cross section of two tubes, so to speak, and they are connected throughout this circumference. And when they go, here you see the protons, they collide. They are made to collide with the use of very, very strong magnets, so that they can first be contained in the beam pipes. Second, they can be accelerated, given a lot of energy, and then focused into collisions at different points on this 27 kilometers. So this is just a picture that is showing you the 27 kilometers on the surface. You see the airport of Geneva on the left bottom of the picture, and you see a dotted line with a plus dotted line. So on the right hand side is France, and on the left hand side is Switzerland. So I am located somewhere close to the airport, not very far. And on the left bottom of the picture is CERN, where exactly CERN is. So yeah, we are looking at scales from the Big Bang to the scale of the galaxies to be able to understand, using this very big microscope underground, 27 kilometers, with our apparatus, to recreate the Big Bang and try to measure something there, right? So these are our protons with the quarks inside, and they go, this is just another picture to give you an idea that this is underground. It is, of course, not on the surface. On the surface, of course, you see the beautiful Alps, you see Lake Geneva, you see the cows in the meadows, but underground, nobody knows that these protons are round and round without their passports, and they change country, every other second or more. Engineering challenge, of course, this is huge. You can see some person here somewhere, I hope, and that person gives you a scale of how big these experiments are. Nothing short of being a space shuttle or a submarine or anything as complex as you can imagine. Our experiment, the one on the bottom right, that's called compact muon solenoid, that is 14,500 tons. Just imagine, 14,500 tons. It's incredible to wonder how it was built in pieces on the surface, and then it was brought underground one by one. All these pieces, each of them weighing anything between 1,000 and 2,200 tons, and they were lowered by means of a special crane. All these kind of technological advances happen in situ. We have, of course, lots of stories on how this was done, but I wouldn't have so much time to go into that. So this is just another view. You see these are the products or the pictures that come out from these experiments. So just imagine the incredible body of work that has been done by these thousands of physicists, engineers, students, doctoral students, who have been busy taking care of one dot in this whole picture. In one experiment, one dot represents a detector, a sensitive piece that has been taking pictures of the collisions. So without going into too much detail, this is just to explain to you the complexity of the experiment. However, it is feasible because of collaboration. And here you see the large number of people working together. Isn't it incredible to imagine that somebody is coming from India, somebody is coming from China, Japan, and then of course Europe is here, United States, South America, and everyone comes together when the inches and the centimeters need to be converted every time you meet, and so on. So and also the versions of the softwares, databases, huge amount of challenges, but then you see people are capable of doing much more when they are working together. And of course, that's the power of collaboration. So
I
these
think these
are just,
moments do
yes.
give us a lot of hope as a civilization.
Absolutely, absolutely. This is the message very clearly said, Pranav, that when we are together, harnessing the power of diversity as well, without articulating it too directly, but you see that this is when we can all come together and do these kind of mammoth tasks. So yes,
That's
looking for the Higgs boson. Sorry.
please go ahead.
Yes, so it's like for looking for the boson or looking for that particle that is responsible for mass is like looking for a needle in a haystack. And yes, it took us an equivalent of 48 years of data taking to find the Higgs boson, because we are taking data 40 million collisions per second. So conversions, don't ask me how, but this is some conversion done by one of my colleagues, and it's incredible how much time it takes to look for that one signal, which looks something like a bump on these pictures. Don't get too carried away by these pictures, or they are not, let's say, too complex. They just explain that above the background, you do see something that is significant. And that has been demonstrated to be the Higgs boson. The Higgs, which is responsible for the mechanism by which particles get mass. Because you might be wondering, why is the electron so light? Why is the proton so heavy? And how do they interact? And so on. So that comes because of this Higgs boson. And on 4th of July, there was a seminar at CERN. You know, this is the conference room of CERN, the largest amphitheater. I went at 5 o'clock in the morning for this seminar, but I did not get a place. I was standing outside in the queue. I had to come back home to watch it online, because this was a very big event where live around the world, the discovery of a Higgs-like particle with a mass of 125, 126 GeV by the experiments CMS and Atlas was announced. And here you see our Director General on the bottom left. That's Fabiola Gianotti and our then spokesperson, Joe Incandela, who are all very, very pleased for this announcement. Subsequently, the next year, Nobel Prize was given jointly to Francois Englert and Peter Higgs for the theoretical discovery. So imagine that they had proposed this mechanism that contributes to our understanding of the origin of mass in 1964. And the discovery of this particle happened in 2012, 2013. So that is the rigor of human spirit and human endeavor, so to speak. And of course, our people, Indian, all over India, in fact, has been working behind the scenes towards this moment when the Higgs discovery was made and it was announced. And these are all people, and as you see, many Indian girls are there as well, professors as well. So this is a very diverse collaboration, and very proud to be part of this collaboration. In addition, we have about 25 girls and women all over the world who are also participating in this experiment. This has been a learning for me as well, to see how people are working in little nooks and crannies in this experiment. And I discovered that there are more than 25 women. This is incredible, isn't it? And then to see that big science in the end of the day wins many Nobel Prizes, it is a measure of success. I agree. It is a measure of success, notwithstanding that we are standing on the shoulders of many giants. That's a photo I'm proud of. Sorry for that. And this is the time when I had just arrived at CERN. And George Sharpak, you see on the bottom left, was the leader of this group called Gas Detector Development Group. And I was part of the group. And I have to tell you of the sorry figure I cut because I had never worked with electronic detectors in India. So that learning that came to be part of this group for nearly 10, 12 years, and the rigor that it gave me in terms of understanding how to work as well has been a very big part of my development, my professional development, and I will always remain grateful to the group in which I landed first when I came from India into this famous group of Professor George Sharpak. Some more pictures just for fun together. That's Professor Aymar on the left. That's, I mean, I'm there as well. And of course, Professor Kalam, who doesn't know. Professor Aymar has been he's an engineer in the CER in France. And then he was also the Director General of CERN when Professor Kalam came to CERN. And I was so fortunate to meet them, and Professor Aymar took me around with him when we had this visit. On the picture on the right, you see again Professor George Sharpak. We was felicitating him at an event that was an IEEE milestone event, which was done in his honor for the Nobel Prize that he got for the multi-wire chambers. And of course, I was a privileged part of this. So now, where do we look forward to? We need to look at the new projects. Because mega science is so global, so international, we absolutely need to look very far. Speaking about 2050, it looks crazy and absurd, but nevertheless, at CERN, people are preparing new projects. Not just one or two people, but a big group of people is already engaged in a project which is called the Future Circular Collider. And on the right picture, you see that the circumference of 100 kilometers is foreseen for this collider. LHC, the Large Hadron Collider of today, was conceived in the 80s, and it's nearly 30 years and 35 years that it took for really coming into cruising mode, and it's still not over. It will run until 2037. So it's the time to engage and to prepare our own capacity and our future leaders. So that's another part of the work that I do a lot, particularly in India, and not only with the boys and shiny smiles you see here, but also behind the scenes where we are able to go to schools to speak about science, to speak about physics, to show them role models like Fabiola Gianotti, who is our Director General. On the right-hand side, you see her. On the second picture on the right, right side, you see she is Charlotte Lindbergh Varakaule. She is our Director for International Relations. And of course, they are very encouraging and they facilitate a lot of the work that we do with a lot of girls. As you see in these pictures, many of them are girls here. And of course, for teachers, they facilitate capacity building. There are many, many programs that go on at CERN. So I'm very involved in that as well. And of course, it's my dream to somehow consolidate and make future leaders who come from India to CERN. So yes, why not women? If we have a planning towards the future, we would look at women leaders in science and technology. So just to show you that whatever we are doing is not just to be very happy because I'm passionate about physics and because, you know, I love doing what I do, which is true. But there are, of course, real life applications apart from WW as well. So you can see here, the WWW has led to the computing grid, which is then used for biology, for education, for meteorology, for weather forecasting, and of course it saves lives and it saves a lot of money as well. In the region where our country is, you know, it is the cancer capital of the world. half of the new cancer cases and cancer deaths worldwide happen in this region, and half of these happen in India. So this is very, very alarming, and we have to look at what we can bring from science and technology to the society. So there are many new techniques that have been spinning off from CERN into society. One of them is for cancer therapy, and that technique is called hadron therapy. You may have heard about proton therapy as well. So won't go into details. If there are questions, we will go into that, just to show you that just like we take pictures of the collisions of protons, we are able to take pictures of our bodies by suitable techniques, and using the detectors that we have detected. We are detecting particles. Here we are able to look inside the body and make imaging pictures. And of course, computing is extremely important, and all this computing that we use in our experiments have direct implications, not only in health. I'm sure your imagination is already running wild on where else can I use all these techniques and technologies. So here is a picture and a doctor's dream, how a doctor without any surgery would be able to look inside the body. And you can see that there is complete deconstruction of the body when you're looking inside it without actually having to do any operation. So this would be fantastic. And on the right bottom is an image that has broken the record of how many hits on the page at CERN. It's after the Higgs boson, it's the next picture that has broken the record. So yes, in the title, there was the word woman, although I would say that for a woman, it's important to speak about work, to speak about her science and her technology. But then it's very important also to realize that we live in this world which makes particularly girls, when they start out their careers, to be confused. And I remember every time I would say I'm doing nuclear physics, people would say, that's unclear physics you mean. Okay, so today I can speak confidently, I hope, but this is not the case when I started my own journey. And like Pranav said, that began in Jhansi. You can see in the center here is a picture from my school. And my very first project that was done when I was in class 10, I built an electric crane, and my teacher, Sister Aquilina, she was amazing. And I think it is her encouragement that led me to be interested in physics in the first place. And then of course, move on to Delhi University. And then of course, eventually to CERN, where I encountered for the first time electronic detectors. And this was my great fortune that I could work in the group alongside Professor Sharpak. Some more pictures of my work. You can see that now when I knew what to do, then we can run the moment you know exactly what to do. So lots of work with small detectors, large detectors, and building collaborations, doing installation, commissioning, and so on. So this has been a very exciting period and a very exciting decade after the first decade of the training that I have received in the group of George Sharpak. So yeah, in the following decade, building detectors, large detectors, you can see here, lots of people are here, and lots of collaborations, by the way. Also, I had so many students in my lab, also from France, from Strasbourg, from Lyon, from Paris, from Nantes, a place in the western part, from Geneva. So yes, at that moment of time, when I finished this big chunk of work, I thought, let me do something different. Let me dream a little more. Let me dare, and let me bring something new to my experiment. And that's when I wrote down a new proposal, which started in 2009. But then, of course, the usual challenges that nobody believes in you and people think that, oh, this will never work. It's already too late. Technology not mature, etc., etc. But then finally, it was approved in 2015. And we started installing, and we started test installations, we started commissioning the detectors, and all this work started then in 2018. And you see in 2019, uh, towards the end of 2019, we installed the first detector in LHC, which means in CMS, which was called phase 2. Phase 2 is just a time difference, which will start when CMS will change its tracker and so on. So not to worry about the terminology, but the first detector, which is an upgrade in CMS, is the GEM detector that I have proposed in 2009. And in 2019, the first half volt. And you see part of the team is here, obviously because of the pandemic. Not everyone has been here in the last years. Oh, wait a second. So here you can see, this is the fully installed GEM. This is completely installed. And the boys are working, the girls are working, and I can. So now I hope you're convinced that if somebody like me can go up the cherry picker, as it is called, you know, these are these very big cranes that go up and down the experiment. I do not, I do remember the moment when I went up this cherry picker, which is 10, 15 meters in height, and you can change the arm, rotating arm, so that you can go and actually do an intervention in the experiment. I remember the first time I went in that basket, I was completely, you know, sweating and wondering, why did I volunteer to do this? Because I thought tomorrow there will be headlines. Archana Sharma breaks the experiment, you know, because this basket of the cherry picker was swinging like this. And, you know, I was shivering, and I was supposed to put one of these traffic cones on top of this experiment as an exercise. And that's when I told myself, Archana, you are a little ambassador. You are a woman. You are India. You do not want that, you know, this will become the headline that, you know, millions of francs have been broken down just because this woman banged into the experiment. So yeah, I mean, these things, there are lots of other stories, but this is something, these are moments that you remember and you will always take a lesson from. And believe me, if I can somewhat do it, you all can run with it. And the skill set that you will acquire when you do particle physics is completely unique, and it offers a multi-dimensional growth. Not as a project manager, not as a coordinator, not as an engineer, as an outreach person, as a communicator. Science communication is extremely important. We need it. People do not know about it. People do not know about the opportunities. We need to go out there and tell young children, young parents, this is the way to go forward. And I can tell you that 70% of the PhDs from particle physics, they end up in banks, in financial institutions, and what have you, in risk management, in space, in astronomy, in astrophysics, and so on. So yes, I hope I have convinced you that it is very important to continue the tradition of curiosity on the shoulders of giant scientists on whom we are standing. We look for opportunities for skilling our own national priorities via international projects. So like Pranav mentioned about French and Indian partnerships, it's a moment now to build these partnerships via the mega science projects and align ourselves with the sustained development goals, because these goals are not just a charter of the United Nations. This is a way of life. We have to see where today good health and well-being is on the highest priority of every government. And that should also be the priority of ourselves as a human being in the society. So let's keep going forward and not only look at our own little corner. The pandemic has demonstrated that the whole planet is connected with each other and nobody can hide anywhere. So I think gender equality is also extremely important. And my personal goal has been, I have to tell you, that in my group, I always have had 50% women and many of them from India. So the goal really would be that wherever I work, I would like to have 50% women in my group, in my team. So I would
That
close.
is initiative.
Yes,
That's really good initiative.
I would just like to refer to Madame Curie, of course, who is the epitome of a woman scientist's dedication, two-time Nobel winner. And she said, I was taught that the way of progress was neither swift nor easy. On m'a appris que la voie du progrès n'était ni rapide ni facile. So thank you very much for your attention.
Thank you very much, ma'am. It was really nice and inspiring to hear from you. For me, especially because I've known you for some time now, and we've had long discussions. But the entire life journey, how you summarize into this 30-minute form is fantastic. So, having said that, I think I have a couple of questions that we might indulge in. But it's so interesting, say, as a science historian to me, that the field, so called high energy physics, started as cosmic ray physics, and particle physics came much later in the 70s and the 80s. Because, as you said, nuclear physics was very, people talking unclear physics and no clear physics, and something of that sort. It was very, it was considered as something what we call string theory now. But like 10 years down the line, when string theory makes a breakthrough, people like me, who are astronomers, will stop saying that. Yeah, but so that's how that's how fields evolve. I mean, it's so interesting, especially in India, and you carry the legacy of those giants. And I must congratulate you how well you've carried it forward. I mean, the interest in India starts with the Cavendish laboratory people coming to India. How H.J. Taylor, people like H.J. Taylor, who were in Wilson College in Bombay, they establish a group in TIFR, and then TIFR starts working. They have people like Pranay Lal, Menon, Bhabha. Bhabha goes to Paris at the same time. Then Julio Curie and Irene, they collaborate here. Satyendra Bose get trained by Madame Curie, and de Broglie was a research assistant there in 24 to 26. All of that was happening, and that gives a little base to what would become the fundamental learning where you start. And of course, it is extremely important to mention the legacy of your predecessor, like Bibha Chaudhary, who did fantastic work. But in the sands of time, there are very few names that survive. So my first question that I would like to ask you is from your new role as a science policymaker. So now you are basically sons envoy to the international organizations, including the United Nations and other places, among other very important roles that you have. My question to you is, ma'am, how do you see the Indo-French relations shaping the future of the field, especially when now India has started opening up to the field? Earlier, it was Kashmir University and Punjab University only who were participating, if I'm not wrong.
Thank you, Pranav, for the very kind comments and all for this question. I think here I would borrow from my collaborators in ITER. There is a very big program that is going on in Kadaresh, which is on creating the largest tokamak on the planet, and that is for making energy from nuclear fusion. So there we have a lot of collaboration and lot of people from the PRL, which is what Physical
The
Research
physical research
Laboratory,
laboratory.
Plasma Research Laboratory in Ahmedabad. Our colleagues are working there. And certainly, I think you made a mention to Bibha. So, of course, we are all standing tall on her shoulders. And Bibha continued, just like Marie Curie, for that matter, on a technique to make visible and invisible radiation. And then she got 3 to 4 publications in Nature also in the 40s. And if I remember well, Cecil Powell got the Nobel Prize in the same field, doing the same work in 1950. So he was standing on the shoulders of D.M. Bose and Bibha Chaudhary, who had together discovered mesons, right? So it is a field which works together with people coming together. And I think Indo-French relationship is very strong. And we need to garner more collaboration, more, let's say, wider participation, because I feel in my humble capacity that people are not aware of the possibilities. You know, you and I are privileged now because we are sitting inside the information gateway, so to speak.
That is true.
And there, so we take things for granted. I can tell
That
you,
is,
I was just fortunate to be thrown into where the roads from where I reached to CERN. I was just
yep.
fortunate, and even then it took me like 10 years to find my bearings. So it takes a lot for an average person from an average city in India to come into, let's say, even the into grips with what's happening abroad. So for the Indo-French relationships, I think outreach, communication, education, these are very, very important.
Okay. That yeah, you made a very interesting point that until unless we do communicate the opportunities thoroughly and openly, rather than an open forum, there's no way. Even when you have, say, like, I mean, the internet revolution and everybody is connected everywhere, it's because of the overload of information. How what geologists would call the age of the Anthropocene. There's so much going on, and there's so much available. There's so much everywhere that it becomes rather difficult to find the right information. You're right. It's extremely important to communicate things in the right order at the right places. And of course, I like your hope for collaboration between Indian and French scientists. Especially, I mean, I have seen how these beautiful collaborations have worked in other fields. My other question, because I have a new role as a science historian now, and I'm training myself. So I ask interview questions for oral history. So my question to you would be, because you were there when all these beautiful things were happening, and when you reached CERN, your mentor in all true terms was George Chapak. Right? So my question to you would be that how do you see the influence of somebody like George Chapak on your work, and perhaps on how you saw him around? And then of course towards and also now that you are almost in the similar position as Chapak, how do you see yourself as a mentor?
Thank you for many questions in one. I think, well, the last question I can answer first. Over the last 10 years, I think I have really given myself into having as much discourse as possible, particularly in India, and not only in India, with younger students. And I'm proud to say that there are so many of the people with whom I let's say interact. They have come under my mentorship. without doing anything, because you lead by example. And
Yes.
I'm not saying, at the moment you set a course, of course your head will be pummeled because you have tried something which is very different from the ordinary. So I mean, I've had my challenges and I continue to have them. It's not that it's over, but it shows that once you have the grit, and once you don't give up, and once you continue to chase what you believe can be done and must be done, there is no way that you will not succeed. So I see behind me so many younger women, first of all, and of course men too. They also have their own challenges, so I'm not going to say that they are like, for them it's a rosy path. No, but I think as a mentor, by an example, example is the biggest contribution that one can do, and I try my best to do that in every way possible. Talking
Hey,
about the group in at CERN when I came, of course, yes.
yeah, please go ahead. Please go ahead.
So in the group, of course, there was not only me, there were about 10-12 people. So the interesting thing was that it's like a family sized group. And of course, for me, it was the very first time that I had actually gone out of India. I had ever taken up an airplane for the first time when I came to CERN. So it was a dramatic change, not only in as if coming to another planet from New Delhi, but also in terms of the culture, on how people worked, how people communicated with each other. I think the mentoring definition of a mentor needs to be looked at. Doesn't mean that somebody is holding your hand and telling you what to do. It's not like that. It is acknowledging that you can do, first of all. That is very important.
Yep.
Facilitating your work, making sure that you are recognized and your contributions are visible. So it's not that I have a mentor, so I am lucky. No, the mentor facilitates, the mentor acknowledges, the mentor makes the road, and you have to walk your journey. So that I saw well in the way things were done, which I have to say that I didn't realize at that time, because everything was so new. Just realizing how to work in the laboratory, because I had never even worked with an oscilloscope before. An oscilloscope is a basic measurement instrument in our laboratory. So those challenges, and that was one of the reasons why I continued to do a DSc from the University of Geneva, because it threw me onto techniques that I must learn. And again, it's the role of being in that environment where day and night we are speaking, eating, breathing multi-wire chambers. That was George Sharpak's legacy. So you get to learn so much just by the fact of being there.
Yeah.
I always say that if a fish grows in an aquarium, it cannot grow to the size of a whale. If you throw that fish in the ocean, if she survives, she will grow.
That's a very interesting observation, ma'am. I have some very interesting questions here for you. One of them, which I found particularly interesting. So the attendee has asked, what tips would you give to 14, 15-year-old teenagers who are considering scientific studies for their higher education? I think this is a very important question to answer.
Absolutely. It's a very good question, very important, as you say, Pranav. The thing is to do would be to go hands-on. Try to find a laboratory near you. Try to look at outreach projects of these large mega science projects that are going on in the country, and see if you can survive being there for a week, for a month, and if it really interests you or not. Because sometimes I remember when I was a kid at that age, if I would see dinosaurs on the TV, I wanted to become an archaeologist. And when I would see planetary documentaries, panorama, and so on, I wanted to become an astronomer. So we need to be sure of what we want to do, and we can only be sure when we do. and doing makes us think more and makes us play more, makes us learn more. So I would go out there. In our country we have many institutions like Tata Institute, like BARC, like IISC, like VCC, RRCAT, universities, ICERs, NICERs. Please go there and talk to professors and talk to teachers. They are all very willing to help and to listen to you if you are really interested in following this path.
That is so true. That is so true. I mean, that has also been my personal experience. If you don't know anything, just ask. I remember as a student in school, I was not really able to understand what the weak nuclear force meant. I sent an email to Steven Weinberg, and in about a week's time, he replied. I
That's the beauty of asking.
half of the world. It's so interesting. I mean, people do. I mean, and that was. I mean, you ask questions and are not able to decide whether to do physics or not do physics. I called up Subir Sarkar. You met Subir Sarkar, and I didn't know what to do. And I called up Subir Sarkar, told him what my dilemma is, and then he says, start somewhere, you'll reach somewhere.
Exactly.
10 years later,
Exactly.
I tell him, see, you told me.
Yeah. Yeah, you're absolutely right. I mean, when I started this new project, I mentioned the GEM project, I didn't know where to start. And
Hmm.
one day I went to my group leader and I was discussing on this project, and he said, "What exactly do you want to do?" So I said, "You know what? I want to bring this new technology to CMS." And he looked at me and he said, "Do." And that was it. And then I thought, what am I waiting for? Let me do it. And of course, and if the earlier you learn, the better it is.
That's true. That is true. Perfect. I think at this note, I think I would like to close today's session. Thank you very much, Dr. Sharma. It was wonderful talking to you. You've been very kind to accept our invitation. And I'm very thankful for the Institute's initiative to host these kind of talks. And I'm glad that we are having this kind of discourse in a public forum. It's very important. And it is also necessary now to bring this kind of narratives, hopeful narratives for people to know, especially in the kind of times that we are living. Thank you very much, ma'am. Thank you very much.
Thank you for having me, Pranav. Thank you.
And for all people who are watching us, we'd be very happy if you could follow the project that we've started. It's the History of Indo-French Scientific Partnership. The blog is hos.ifindia.in. Thank you very much.